Professor Muhammad, and this is a new course or a new video in our series for engineering mathematics. So let me use this pointer, and we are going to talk today about the solution of initial value problem using Laplace transform. Okay, now let's go to this. Actually, today we are going to, as I said in the title, we are going to focus on the initial value problem. This is our main target, and we are going to solve it using Laplace transform. So this video is going to show us some techniques for the solution of initial value problem using the Laplace transform. Okay. Let's have an introduction here. I hope that it will help us to understand what's going on after that. To apply the Laplace transform to the solution of an initial value problem, we must be able to transform a derivative, which is the derivative of the function. This is the meaning of the derivative. It is the derivative of the function. We want to transform the derivative of the function. Usually whenever that we have y of t, we can transform it in order to get y uppercase of t, which is the Laplace transform. But sometimes we want to obtain the Laplace transform of that derivative. We want to get Laplace transform of the derivative of the function. So how we are going to obtain it? So we need to know how to get this transform of the derivative. Before indulging into this point, we need to define an important concept which is related to a function called piecewise continuous function. So in order to understand how to obtain the transform of a derivative, we need to understand the concept of piecewise continuous function. Okay? Okay. So now let's go and understand what is the meaning of this. Suppose that we have a function which is f of t is defined at least on an interval which is a and b, between a and b. Then f, which is the function itself, is considered to be piecewise continuous on this interval f. We have three conditions here. We have three conditions. Condition number one, if this function, which is f of t, is continuous at all but perhaps finitely many points of a to b on this interval, means that if our function is continuous, if the function is continuous on this interval, then our function is piecewise. And this is condition number two. If the function f is not continuous at t node, any point on the interval called t node, in a, b, take care here, the parentheses, they are like braces here. They are not like rectangular braces here. Means that inside the interval itself. Here a and b, it is including a and b because of these braces. Okay, but this parentheses or these curly, I'm not sure this is curly or not, but this is like the half, like half of the arc or something. Then this means that inside the interval. Then f of t has finite limits from both sides of t. Then if we have a discontinuity at point t node, but we are having a finite limits from both sides at t node. I'm going to show this shortly, okay, in the next slides using some graphs, so do not worry about this. And f of t has a finite has finite limits as t approaches a and as t approaches b from within the interval. So this one is related to the approaching the limits of the interval from within the interval. Let's have an example to understand it. Okay, look at this function. This function, we can call it as like piecewise function. What is the meaning of piecewise here? This function that is graphed here has jump discontinuities at point t node and t1. Okay, as you can see, we have some discontinuity. So this is the function here is smooth, but at some points at t node and t1 it is discontinuous. The magnitude of the jump here, okay, is the width of this gap, okay, and this magnitude is going to be the absolute value of what? If we say that this point minus this point, right, it will give us the difference here. This point is what? Actually, it belongs to this part of the function, right? So we are going to say that at any point t1, whenever that we're talking from the right, we are going to give it a designation which is plus, positive, and whenever that we're talking about from the left, we're going to give it the designation of minus. So this is right, okay, and this is left. It's only a kind of like convention to tell that at this discontinuity what is the approaching side. So if we put it positive, this means that from the right. If we put it negative, this means that approaching from the left. So we're going to say that the absolute difference, as you can see here, between the function f of t when it approaches t1 from the right, this is t1, and approaching it from the right, which is from the positive here, right, which is here. This is the function, and this is the point where that the function is going to approach from the right, minus the same function when it is approaching t1 from the left, because there's minus here. This is t1, and this is the left of t1. So when the function is approaching to this point here, right, the absolute difference between the two is going to be this gap. Okay, so this is a typical function for piecewise continuous function. Why? Because it is continuous on each part within the interval. If we are telling that the interval from here to here, for example, it is continuous, and if there is some discontinuities, as you can see here, this discontinuities is approaching to a certain point, certain value at the ends, right? So this is going to clarify point number 2 here. If f is not continuous at t node in this interval, then f of t has finite limits from both sides at t node. Let's go and see this. This is t node, and there is finite. Finite means that there is specific value from the left, from the right, which is positive, and here, which is from the left, which is negative. This is a finite value. We know this value, how much it, and we know this value, how much it is, right? So this t node, it is considered to be satisfying condition number 2, right? Finite limits from both sides at t node. Similarly, we can apply it at t1. T1 we have finite value here and finite value here. From the right and from the left, it is okay. Okay, now let's go to the third one. If t has finite limits at t approaches a and as t approaches b from within the interval. So let's assume that we have here, this is point A, this is the maximum interval, and this is b here. This is the limits of our function. The limits of our function here, when we are approaching to this a, we find that there is a value here, right? And when we are approaching to this b limit, we can find there is a value here, right? So let's go back. F of t has finite limits as t approaches a, which is the first limit of the interval, and as t approaches b, which is the second limit of the interval, from within. This is the key word here, from within the interval. So based on this, this function is piecewise continuous function. Okay? Piecewise continuous function. Now let's go to another case where that our function is not a piecewise continuous function. Let's go to this example. We have g of t equals to 1 over t for t larger than 0 and smaller than or equal to 1. So here we have between 0 and 1, but without inclusion of 0, it is 1 over t. So this is our function here. This is our function, which is 1 over t, starting from 0, but without considering 0, okay, until we reach to 1. This is our function. And it equals to 0 when t equal to 0. When t equal to 0, then the function is going to be 0. Okay? So this is the function for us, which is in red now, and this point here, which I put it. Now then, g is continuous on 0 to 1. Take care, 0, it is the vertical brace here, and this is the arc brace here. This means that 0 is not included, but is not piecewise continuous on, yes, on the function. Why? On the interval 0 to 1, including 0. Why? Because when we are going to approach this function from the left, it will approach to what? Yes, here, infinity. It will be infinity. It will be 1 over infinity. Sorry, 1 over 0. I'm sorry. It will be infinity, right? This because here, if we are going to put this t as 0, as it is approaching 0, as t is approaching 0, this means that g of t is going to be infinity. And this is what we have put it here. So the limit, okay, of our function g of t, where t is approaching to 0 from the right, here, it is going to be infinity. Then this function is not a piecewise function. It is not a piecewise function. Why? Go to the conditions. Yes, because condition number 3 is not fulfilled, which is f of t has finite limits. At t approaches a, the limit, our a in our example was 0, right? And as t approaches b from within the interval, then our case that when it approaches 0, it doesn't have finite limits. It was infinity in our case. Okay? So this is a example of not piecewise function, and the previous example, this is an example of a piecewise function. Okay, now let's go to the theorem, transform of the derivatives, which is our main theorem now. Our main target, remember that we want to obtain the transform, Laplace transform of the derivative. So we are going to say, easily, we are going to say that let f be continuous for t larger than 0, and suppose that f prime, which is the derivative, is piecewise continuous. Take care, you understand now fully what is the meaning of piecewise continuous. If our f prime is piecewise continuous and our function is what? Yes, take care, continuous only. It's not piecewise continuous, only continuous. A function that is continuous, okay, but not piecewise. For f prime, it is piecewise continuous. On an interval 0 and k, with the inclusion of 0 and inclusion of k, because of the vertical braces, for every k larger than 0, which is this limit is larger than 0, it is positive. Suppose also that limit of the f of k, the function at k multiplied by e to the power minus sk, where it is approaching infinity, equal to 0. This is a kind of condition. Okay? Do not think too much about this condition. We are going to understand the procedure later. If s larger than 0, then the Laplace transform of the derivative is going to be s times Laplace transform of the main function minus the function itself at point 0. Take care, this is f uppercase, this is lowercase. This is Laplace transform, this is the function. Okay? This states that the transform of f prime of t, the derivative, is s times the transform of t minus f, the function, at 0, which is the original function evaluated at t equal to 0. This can be proved by integration by parts. You can prove it easily. You can see problem 11 in the textbook. It is a problem. You can solve it by yourself if you want. The derivation is not a big deal. Okay, just for illustration, you can go to this problem and you can solve it by yourself. You're going to find that what we are saying here is true. Okay. Then ff has a jump discontinuity at 0, as occurs if f is an electromotive force. In case of electromotive force, we're going to find this kind of functions are commonly used. So that is switched on at time 0, then the conclusion of the theorem must be amended to read. It is a kind of amendment for this main function or this main theorem, that Laplace transform of the derivative would equal to s times Laplace transform of the function minus f times f, the function of the 0 from the right. Okay, take care. This is important to only for this case, for those who are going to work for electrical major or field, they are going to understand this clearly and they will use it many times. Okay, but anyway, for us we need to focus on this part. Okay, I'm going to erase all of the things here. Yes, this is our main function that you need to remember well. Okay, this is what I want you, so you can't forget everything here in this page. You can't forget everything, just I want you to remember this, that the Laplace transform of the derivative of the function equals to s times the Laplace transform of the function itself minus the function evaluated at 0. Okay, this is what I want you to remember. Okay, okay, now let's go to the next part. If we have a higher derivative, we want to obtain the transform, Laplace transform of a higher derivative. So let's assume that we have f and f prime and fn minus 1. These are like the derivatives of the function. Be continuous for t larger than 0. They are, all of them, they are continuous for t larger than 0. And suppose that f of n, that f with the derivative n is piecewise continuous. So all of them, all the derivatives are continuous, except the last one is going to be piecewise continuous. Okay, this is similar. If you go back and this, do you remember this? We started if b is f is continuous and f prime is what? Piecewise continuous. The last derivative that we're going to talk about here, it is the first derivative, then it should be piecewise, and the function, which is the less one derivative or the original function, it's continuous. Here, similar. All the derivatives, including the function, is or are continuous. However, our last derivative, f raised or fn derivative with n derivative, it is piecewise. Okay? On this interval 0 to k, for every k which is larger than 0, suppose also that this is fulfilled, that the limit of e to minus sk times f of j k equal to 0 when k approaches to infinity. This is for s larger than 0, and j from 1 till n minus 1. Take care, it is n minus 1, not n. Then the Laplace transform of the n derivative of the function is going to be like this. S to the power n f of s, which is the transform of the function, minus s raised to minus n to minus 1 raised to n minus 1 times f of 0 minus s raised to n minus 2 times f prime, and so on and so forth until that you reach f of or n minus 1 derivative of the function multiplied, evaluated at 0. What I want you to remember from this story is the coming part, which is the case where that the second derivative, whenever that we have f double prime. This is most commonly what you are going to see in our examples and problems. So you need to focus on this. If you do not understand this point or this derivation, don't worry about it. Okay, don't worry about it. Just worry about this part. Remember this part, which is the second derivative Laplace transform. In the second derivative Laplace transform, it equals to s squared times the Laplace transform of the function minus s times the function evaluated at 0 minus f prime of the function evaluated at 0. This is what I want you to memorize. You need to memorize this function or this equation, okay? Remember, this is equation 3.3 in the textbook and very important, and this the most important one also is 3.1. These are the most important two equations that I want you to remember when you are dealing with this part. Okay? Okay, so let's go and jump directly to an example to understand what we are doing. Remember that we want to solve what? An equation, differential equation, which is this equation, for an initial value problem. So we are talking about IVP, initial value problem, using Laplace. Now it is everything is going to be clear for you. Okay, so actually this equation already we know it. Let's go back here. Yes, this equation, which is y prime minus 4y equal to 1, we can solve it easily by our techniques, but we are going to apply Laplace transform and the inverse of Laplace transform to understand how we can apply and how much ease Laplace transform is providing for us. Okay, now we're going to look to this left hand side, which is y prime minus 4y equal to 1. Let's take Laplace transform of the two sides, the left hand side and the right hand side. So Laplace transform of y prime minus 4y of s, this is our variable, equal to linearity. We have the linearity of the Laplace transform, which means that Laplace transform of y prime, which is the first term here, minus 4 times Laplace transform of the function, right? So this means that we put it on the letters uppercase here, which is s, y of s, minus y lowercase of 0. From where this? From equation 3.1, from the previous slides. The Laplace transform of the derivative equals to s times f of s of the function minus f, which is the function itself evaluated at 0. We have here, this is the derivative, then we're going to put it like this. We are going to decompose it sy capital of s minus y small at 0. And this 4 times Laplace transform 4ys, right? Equal to the right hand side. We have the right hand side here is 1, right? So Laplace transform is 1 is very easy. Laplace transform of 1 is what? 1 over s, right? Okay. Now we know y of 0 equal to 1. This is an initial value problem and they give it to us. Then we can rearrange and insert y of 0 equal to 1 and use the table to find Laplace transform of 1, which is 1 over s. Then we are going to, after rearrangement, we're going to find s minus 4, y capital of s minus 1 equal to 1 over s. So this is, now if you look to it, It is what? Exactly, it's algebraic equation. There is no derivatives here. You cannot see any derivatives. Okay, this is the magic of the Laplace transform, or the derivative of the Laplace transform. There is no derivative in this equation. Laplace transform has converted the differential equation into algebraic equation for the transform y of s. Now this is algebraic equation only in y of s, right? It's very easy to solve. Now we're going to rearrange y of s, put it in the left hand side alone, and put in the right hand side the two terms, as you can see. Now we can use, now remember, this is what? Laplace transform of the function. We want to solve our main differential equation. This means that we want to obtain lowercase y. Okay, this is what we want. We want lowercase y. Okay, so we need to take what? Exactly. Inverse Laplace transform of this equation from the both sides, and we can get y. Okay, so this y of s capital is going to be changed to y small. Okay, now let's go. And remember, this is our Laplace transform table. We're going to recall and we are going to revisit it again. So now let's go. This is our equation. Now this is the transform of the solution of the initial value problem. The solution is y of t. Remember, this is our solution. We want it, which we obtain by applying inverse transform. Y of s, take the inverse transform. For the left hand side, this would be Laplace transform of y. It is going to be equal to the right hand side transform. Laplace transform inverse L of 1 over s minus 4 plus 1 over s times s minus 4. From entry 3, from the table, this is entry 3, and you're going to find that here what is happening is 1 over s minus 1. 1 over s minus, sorry, a. This is a, so a is going to be 4 here. This means that this Laplace transform inverse is going to be e to the power 4t here, right? And for the second term, we have 1 over s times s minus 4. Two terms multiplied together, and s is there. From entry number 5, this is entry number 5, you're going to find in the denominator two terms multiplied together, right? This means that our term, the first one is s, means that it suggests that a is going to be 0. That's right. A is going to be 0. And the second, it is s minus 4. This is s minus b. So b is going to be 4. That's right. b is going to be 4 here. Okay? This means that our Laplace transform for this, the second term, is going to be 1 over minus 4, because we are going to, exactly, we have here a minus b, which is 0 minus 4. So we need to multiply by 1 over minus 4 in order to remove the numerator. And then we're going to say that it is going to be multiplied by e raised to exponential function raised to 0t. This means that here this is exactly 1. And then minus e to the power 4t. Rearranging, we're going to find that it is 1 over 4 times e to 4t minus 1. This is the second term. So the first term is e to 4t. The second term is this term. So we're going to put it here. First term, and this is the second term. And what is the left hand side here? Exactly, it is the Laplace transform of the inverse of Laplace transform, which is y small, lowercase y. This is what is going to be here. Okay. Rearranging, you can obtain that at the end y equal to this values. 5 over 4 e to 4t minus 4. Okay. This is the final result for us. So let's go back to understand what we have done. Here we started with a differential equation. We applied our theory, which is equation 3.1, to transform this differential equation with y prime and so on, we change it to what? Exactly, algebraic equation in the Laplace transform. So we transformed the differential equation to algebraic equation in the transform, in the Laplace transform. And then using the table, we can look to the right hand side and take the inverse of the left hand side and the right hand side, inverse transform. Using the table, we can obtain, so this is the inverse of the first term, and this is the inverse of the second term. Then easily we can use our table that we are familiar with. Then we can find that at the end our equation, so the left hand side is going to be the answer, which is y lowercase of t, and the right hand side is going to be solved easily by the table, from the table. Okay. This is the flow chart of how we can use Laplace transform to change or to transform our differential equation into a algebraic equation, taking into consideration the equation 3.1, which is the derivative of Laplace transform. Okay. Now let's go to the next example, which is going to be a little bit higher than before in terms of the derivatives. We're going to find y double prime plus 4y prime plus 3y equals to e to t, and it's an initial value problem. We have y of 0 equal to 0, y prime of 0 equal to 2. Remember, we have, this is equation 3.1, and this is 3.2, I guess. I'm not sure. Sorry, 3.3. Okay, which is the equation for the second derivative, Laplace transform of the second derivative. Here, Laplace transform for the first derivative. Okay. Now we have second derivative, we have first derivative. Okay. Now, using the linearity of Laplace transform and equations 3.1 and 3.3, we can obtain, take the Laplace transform of this differential equation. So L of y double prime plus 4 times L of y prime plus 3L of y equals to Laplace transform of e to t. Okay, Laplace transform of e of t, which is the right hand side. It's easy from the table, you can obtain it easily. 1 over s minus 1. This is the right hand side. Now let's go to the left hand side. We have y double prime. What is the Laplace transform of y double prime? Exactly, look to this equation. S, f of s minus s, f small of 0 plus minus f prime of 0. S squared y capital minus s y small of 0 minus y prime small of 0. Exactly the same. And here plus 4 plus transform of y prime, which is equation 3.1, s times f of s minus f of 0. S capital Y minus y small of 0 plus 3 of y, which is the same. Rearrange it, and you are going to find that it is going to be algebraic equation in y. Can you see here? This is the equation. This is what's supposed to be the left-hand side here. It is only algebraic equation, and the right-hand side is going to be something related to s. Rearranging both, putting the Laplace transform, taking it as a common factor here, and put everything on the right, then you are going to find that after rearranging, you are going to find this is the right-hand side, and this is the left-hand side. Okay, so we now have Laplace transform on the left-hand side clearly equal to the s, which is our independent variable s. Now we want to solve this. This is easily can be solved from the table. Now let's go and see how we're going to solve it. Look to the right-hand side before here. We have, it is a little bit complicated here because we have 3 terms multiplied together in the denominator, right? So how we are going to overcome this? We're going to use a technique here called partial fractions decomposition. What is the meaning of this? We're going to take this right-hand side with the three terms, multiplication on the denominator, and we are going to say we have 1, 2, 3. Then we're going to have 1, 2, 3 terms. Every term is going to take one of the denominator term. Here is minus 1, here is plus 2, plus 1, here is plus 3, as you can see it. Okay, so this is the first part, and the numerator for each one is going to be a, b, c. Like variables, we do not know them. Then from the decomposition means what? That the numerator here is going to equal the numerator that is going to be created here, right? What is the numerator here that is going to be created from these three terms? It is going to be a times s plus 1 times s plus 3. A plus times s plus 1 times s plus 3 plus b times s minus 1 times s plus 3 plus c times s minus 1 times s plus 1. Okay, these are the three terms. It equals to what? The left-hand side numerator, 2s minus 1. Well, what will happen here? It seems that we have a, b, c. It is a very long equation, and it seems that it will not be solved. No. It will be solved easily now. Look here to the right-hand side. If we are going to put s equal to 1, put s equal to 1, s equal to 1. So s equal to 1 here, this is 0. This means that this term will vanish. S minus s here 1, this term would vanish. And this term is going to be a times 1 plus 1 times 1 plus 3. So here it will be the remaining term, and it would equal 2s minus 1. We can solve it for a easily, right? So if we put s equal to 1, we are going to get 8a equal to 1 actually. 8a equal to 1 because s here is going to be 1. Then we can obtain the first parameter or constant, which is 1 over 8. Similarly, let's erase everything here. Similarly for this term, we are going to put s equals to minus 1. If we put s minus 1 here, this means that this term is going to be 0, this vanish. And if we put s minus 1 here, this term is going to be 0, then this vanish. And we are going to remain with b times minus 1, which is minus 2, minus 1 plus 3, which is 2, and then the multiplication we're going to obtain. Here it is going to be 2 times minus 1, so we can obtain b easily. It is going to end up with minus 4b equal to minus 3, and b equals to 3 over 4. In a similar fashion, if we put s equal to minus 3, so you are searching for something that makes the other two terms to be vanishing, and the only remaining term is going to be there. This would happen if we want to get rid of b and a. This means that s needs to be minus 3. So we will get rid of this and this term. And then here, it will be 3, right? Minus 3 here, minus 1, and minus 3 plus 1. It will have a value here, which is 8c. And the right-hand side is going to be 2 times minus 3, minus 1, which is minus 7. We can obtain c equal to minus 7. So now we are going to substitute in the original equation. And it is going to be the left-hand side for us is y of s capital, it is Laplace, equals to 1 over 8, which is a, times the first term, which is 1 over s minus 1 here, plus 3 over 4, which is b, times 1 over s plus 1, 1 over s plus 1, and c, which is already we have obtained it, minus 7 over 8 minus 7 over 8 times 1 over s plus 3, which is this term. Now it's very easy for us. Now look to this, 1 over s minus 1. From the table we can obtain it. Yes, e to the power t. And this is 1 over s plus 1. It is going to be e to minus t. And this is 1 over s plus 3. It is going to be e to minus 3t. Okay, so they are... Now we have solved this because this is the inverse. We're taking the inverse of this equation. This means that the capital Y is going to be lowercase y, and this is the solution of our equation. This is the solution of our equation. Okay. Now let's go to another part, which is the shifting and the Heaviside function. The shifting and the Heaviside function. What is the meaning of this? It's a very simple concept, just I want you to know about it. That we are going to say here in the shifting theorems of this section, we will enable us to solve problems involving pulses. Actually, this is the main purpose. The main purpose. Pulses and other discontinuous force functions. So if some students are going to work for electrical engineering or going to major in electrical engineering, then this is going to make sense for them. Okay? So we are talking about whenever that we have pulses or discontinuous function, this part is going to help them. The first shifting theorem, we will show that the Laplace transform of e to at times f of t is the transform of f of t shifted a units to the right. This shift is achieved by replacing s by s minus 1 and the Laplace transform of the original function to obtain f of s minus a. Maybe you do not understand. I guess that you didn't understand it very well, right? But remember that we're going to take an example and you are going to find it super easy. Okay? So let's put this theorem, first shifting theorem. We're going to find that for any number a, e to at times the function is going to Laplace transform of this e to at times the function is going to equal the Laplace transform of s minus a. This is the shifting theorem that we call it. Shifting because as if that we are shifting the variable s, a value of a. That's the meaning. Actually, from where we got this? It is from Laplace transform. Do you remember Laplace transform definition? Laplace transform of the function equals to the integration that we wanted to converge from 0 to infinity, e to minus st times f of t. Right? So here we are telling that we have e raised to at, which is this term. This is from the definition, times f of t. So we're going to have from 0 to infinity e to minus s of t times e to at. Right? This is our main function. This is the definition from the Laplace transform. Just we multiplied by EAT here. So when you put it, you're going to find that here it is e to minus s minus a times t. There is t here. Huh? Take care, there is t here. F of t. You're going to find it missed in the textbook, I guess. So here, this means, what is this? It is Laplace transform of variable called s minus a, because we have here s minus a, right? So remember the definition of Laplace transform, and you are going to understand this definition and this results very well. Okay, now directly let's go to an example to understand it. We know from the table that cosine, the Laplace transform of cosine beta t, bt, it equals to s over s squared plus b squared. Please check it from the table. And this is Laplace transform of cosine bt. For the transform of e raised to at times cosine bt, we are going simply to replace s with s minus a. That's it. Okay? that's what we are going to do. So Laplace transform of this function, which is EAT times cosine BT of S, it equals to, and instead of S, it is going to be exactly S minus A. And here it is S, it is going to be S minus A. That's it. And B, it will be the same. Understand it? Okay, let's have another example to see that how much it's super easy. That Laplace transform of t raised to the power 3 equals to what? The factorial of n over s raised to n plus 1, right? This is from the table. So this t to the power 3 means that Laplace transform is 6 over s to the power 4. Then our function is going to be simply would be t, which is our main functions, times what? E to 7t, right? So a here is going to be, this is our case based on our definition for the function, which is t to the power 3 times e to 7t equals to 6 over s minus 7 to the power 4. Just shifted the function from s to be s minus 7, or the independent variable from s to be s minus 7. Okay, you understand it? Okay. So this is actually, the point here is that seems to be very easy and simple and straightforward. And you are going to find that how much it's easy whenever that we are going to solve the equations or problems that is involving any kind of pulse functions or something like this. Okay. So the point is every formula for the Laplace transform of a function is also a formula for the inverse Laplace transform of the function. The inverse version of the first shifting theorem is, if we're going to take the inverse Laplace transform of the first shifting theorem, then it will be inverse, which is L raised to minus 1, f of s minus 1. This is the first shifting theorem, right? Then what is the inverse of it? Exactly, it is going to be e raised to at times the function itself. That's it. This is what we are going to have. So this would help us very much in the solution, as we are going to see here. Okay, now let's go and solve this example in the textbook, which is 3.6. We want to get the inverse Laplace transform of this term, which is 4 over s squared plus 4s plus 20. The idea is to manipulate the given function of s, this is the given function of s, to the form of f of s minus a. That's the point for some f and a. What is the meaning of this? We want to change this denominator, instead of being like s squared plus 4s plus 20, no, we want it to be something like this. S minus something, s minus constant. That's our main target. Then you are going to find that it's very easy and simple to get the inverse transform. Then we can apply the inverse form of the shifting theorem, which is this one, which is equation 3.5. And we can complete the square here of the denominator to write this in the form of s minus a. Let's see. It is s squared plus 4s plus 20. Is it possible to write it like this? That is s minus 2 to the power 2. Is it okay? I'm just manipulating this two terms. I'm going to put it here. S minus here, it means that s plus 2 raised to the power 2. And of course, if you are going to decompose this, because it's raised to 2, you're going to find there's 4 here would be there. So the last term here, it should be, instead of 20, it should be 16, right? Then a is going to be minus 2. Then our Laplace transform is going to be s plus 2. S plus 2, because this is here. So our a, as I said, a equals to minus 2. Then f of s, of our function, now we are going to make what? the the shifting theorem. The shifting theorem. So f of s equal to what? This is what we know from the table. That is, if we have 4 over s squared plus 16, okay, from the table, this is what we are having in order to make the first shifting theorem. So s plus 2, it is going to be changed to s only because we are obtaining the Laplace transform of the function, okay, before the shifting. From the table, f of s has the inverse of f of t sine 4t, right? This is from the table, you can obtain it. 4 over s squared plus 16 sine 4 over 4t from the table equals to 4 over s squared plus 4 squared. This is from the table. This is from the table. You can obtain it from the table. Okay? Then the inverse transform of the original function is going to be 4 over s squared plus 4s plus 20. We have proved that it equals to Laplace transform of s plus 2. So it will be the inverse Laplace transform of f plus 2. And this would equal to what? E to at. As I said, a here is what? Minus 2. So e to minus 2 times t times f of t. What is our f of t? It is sine 4t. Right? Sine 4t from the table. As we said, Laplace transform of this function. So the point is, this first shifting theorem, Laplace transform of the first shifting theorem, is going to be an easy tool for us to obtain the final answer through the Laplace transform of using or applying the Laplace transform of the first shifting theorem. Okay, you understand it now? I hope that using this equation and using this example, you are going to understand what I have explained regarding the theorem or the first shifting theorem. Again, I'm going to recap what I've said. Our main idea is we can make shift in the independent variable by taking the Laplace transform of the function itself multiplied by something called e to the power at. That's it. This is what we are trying to keep. Okay. Then we found that the Laplace transform of this shifting theorem is going to give us our function, right? So if we have something here and it is the Laplace transform, if we take the inverse of it, which is easy for us to obtain using the table and so on, we can obtain the function itself times e to at. It will be easy for us to solve. And we have seen through this example, we want to get the Laplace transform of this function. We found that this function seems to be a little bit difficult. So we changed the denominator to be something that is easy to be similar to this, similar to s minus a. Okay, that's the point. So we manipulated this denominator and we put it as s plus 2 to the power 2 plus 16. It is okay. Now, if this is our main independent variable shifted by 2, then this is the first shifted theorem, or this is Laplace transform of s plus 2, right? Because here it was the inverse. So inside it is going to be Laplace transform. So this is Laplace transform of the, not s, but the shifted s, which is s plus 2, right? Okay. So now this 4 over s plus 2 to the power 2 plus 16, this is what? This is after shifting. Now let's go back to our original Laplace transform without shifting, which is f of s. It is going to be 4 over s squared plus 16. So this is what it is easy to obtain from the table, right? This is the table here, sine 4t. This is the Laplace transform of the sine 4t. Then we obtain this Laplace transform. Now, then we are going to solve this equation by using this Laplace transform inverse, Laplace transform from the table. Now, Laplace transform inverse of the original function that we have here is going to be L minus 1 of what? F of s plus 2. This f of s plus 2 is very easy for us. Remember that here. It is going to be the function times e to at. It is going to be the function, our f of t, which is sine 4t here, times e2 minus 2t. Take care, a equal to minus 2. Right? So this is what we have done in this example. Now let's go to the next example, which is compute Laplace transform, the inverse Laplace transform of 3s minus 1 over s squared minus 6s plus 2. Only take care and remember in the table we are going to use sine and cosine at. It equals to a over s squared minus a squared, and cosine at equal to s over s squared minus a squared. Okay. Follow the strategy of the previous example 3.6. Manipulate f of s to a function of s minus a. That's the point. We want to change this to have something like this, s minus a. Okay? So we're going to manipulate this. Look here in the denominator. We're going to say that this denominator can be decomposed as s minus 3 to the power 2 minus 7. Right? That's right. This is exactly the same as this one. Okay? Then it is going to be here, this is s minus 3 to the power 2, and here we are like manipulating this, and instead of 3s minus 1 we are going to put it like this: 3s minus 3 plus 8. This would give you 3s minus 1, right? So now we have what? S minus 3 here. We have s minus 3. Okay, this means that there is shifting in s. Shifting in s. We are going to decompose it into two terms. So the first term is 3s minus 3 over the same denominator, and here 8, this one, over the same denominator. Now this is easy to be, look to it, 3s minus 3 over s minus 3 to the power 2 minus 7. Right? So now, can you look to this? Remember two things, that we have the inverse transform of this function. Okay, look to this. It is s shifted by 3 units, right? So we can say that this function is going to be this function s minus 3, okay, is going to be e to at times the function itself. But here this is for the inverse, right? So we are going to put it like this: e to 3t, 3 here, it is a, the amount of the shifting. Okay, remember this is a. Okay, so e to 3t, the inverse transform of 3s over s squared minus 7, because we have multiplied e to 3t times the, as if this is the inverse of the function itself, right? Similarly here, e to 3t times the inverse of the function, Laplace transform of the function itself. So instead of s minus 3, it is s squared. So the point is, we remove the shifting here and shifting here and here, and put e to 3t outside based on this equation. Remember this equation. So now this is from the table, is very easy to be obtained. This is cosine square root of 7 times t. And this is going to be sine square root of 7. That's it. So this is the inverse the inverse of this function is going to be, as you can see here. Okay, again, what I have done is step number one, let's erase it, and step number one, manipulate the numerator and denominator to be something that we can have a shift in it. So here we said that s minus 3, and in the numerator we put s minus 3. That's very nice. After that, we decomposed it two terms so that it will be easier for us to use the table and find the inverse for them. Then what we are going to do, we're going to take the Laplace inverse Laplace transform for both of them. But we have the shifting theorem, inverse Laplace transform of the shifting theorem. We know that if we have Laplace transform of s minus a, it would equal to the function itself times something called e to at, and this a is going to be the shifting value of our function. So we put it in this term. We say that 3s minus 3 over s minus 3 times 2 minus 7, we can remove this s minus 3 and s minus 3, we put it as s only. And what will happen, we'll put e to 3t, remember here, right? And similar here, we are going to remove this s minus 3 and put s, and we're going to put e to 3t. From where? From this shifting theorem. Take care, we're talking about the Laplace inverse Laplace transform here, right? Okay, so here we're going to have the inverse Laplace transform of the function itself, e to 3t times the inverse of the function, or as if we're talking about the Laplace transform of the function itself, right? Okay, now from the table you can obtain this cosine and sine, okay, from this table that we have. Okay, the last thing is the Heaviside function and pulses. We're going to talk about them. So here the Heaviside, actually this is something that, as I said, there is no application except for electrical engineering major. That functions having jump discontinuities are efficiently treated by using unit step function. We call it unit step function, or we call it Heaviside function f, which is defined by, sometimes we want to turn on and turn off some function. So we define this function, which is h of t. 0, it equal to 0 for t larger than, t less than 0, and equal to 1 when t is larger than 0. It is similar to this. This is what we call it the Heaviside function. Heaviside function. Let's have a bigger value here. This is the Heaviside function, that the function is 0 until certain point, then it is going to have jump discontinuity and then take value. So it is going to be 0, 1 or 0. Okay, so this is what we call it the Heaviside function. Another one is, we call it the shifted Heaviside function, h of t minus a, which is going to be, this is the Heaviside function shifted a units to the right. So h t minus a equal to 0 for t less than 0, less than a, which is here, this is 0, 0, 0 until t equal to a, and then it equals to 1 for t larger than or equal to a, which is the limit here. Let's have a larger look. This is a here. So the function equal to 0 until a, and then after a it is going to be 1. As I said, it is like turning on and turning off. It is like the switch. This is what we call it the Heaviside functions here, or shifted Heaviside function, or the shifted, or the Heave function. It's like the switch for any function. Okay. So this is why we can find h of t minus a can be used to turn a signal off until time t, and then to turn it on. So this is very famous in electrical engineering and those who are going to major in electrical engineering. In particular, we can say that if we have a function g of t, if we multiply this function by h of t minus a, then it is going to give us 0 for t less than a, and it's going to give us the function for t larger than a. So this is like, as I said, turning on or off the function. Okay, and we can illustrate this in this way. This is the function for, this is the figure for function cosine t that is controlled by h of t minus pi. Okay, so we're going to find that the function is almost 0 here, 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 until that it reaches to this value, then, which is pi, then it will start to work now. Okay, then this is what we call it the shifted Heaviside function. Okay, and then we can also use the Heaviside function to define what we call it the pulse. This is commonly, as I said, in electrical engineering, if a less than b, then we can find ht minus a minus ht minus b equal to 0 for t smaller than, less than a, and equal to 1 for t between the interval a and b, and equal to 0 again for t larger than b. It seems like that you are controlling over a certain period of time the function would work, and then the function would not work after that. That's it, and there is no examples or problems that you should solve regarding this. This is only for your information. It's not very important for us or even in the exam. Okay, this is only for your information. Okay, that's it for today. Thank you very much, and see you in the next video.